the floor for question. So let's start. Any question? Please.
Thank you very much for your interesting talk. I have a question about what's your estimation about the thickness of that in nanoglass? Thickness of the interface, glassy interface. I think the difference between the non-glassy phase and the nanoparticle glass also interface should be due to something like density, I guess. But what's your estimation about the thickness of this interface, and also if I change the size of this nanoparticle glass, what is the effect of this change of size on the changing of the thickness of the interface?
Yeah, what I can show you perhaps what we can see. Big glasses and small glasses is always apparently what is important is that the free energy, the free volume which is caught in the interface gets smeared out so that the nanoglass can form this layer. Yeah. Here you can see a little bit. This thing they have a size of about 5 to 6 nanometers, and here is the interface. And as you can see, it's such a thing. So it's a uniform thickness, about 2 nanometers in size. What we do not know at the moment is what the atomic structure is. The reason is very simple. In order to do ab initio calculations, you have to know where the atoms sit, but we do not know where they sit exactly at the moment. We are doing some experiments, but if we would know that, then we could do the electronic structure. But to get the electronic structure, you have to know where the atoms sit, and in order to know where the atoms sit, you have to know the interaction between the atoms. So all what we can say is densities, modulus, electric conductivity. We can always get kind of a result which averages, but we do not know where the atoms in principle sit. What we are doing at the moment is we go with a microelectronic beam with a diameter of about half a nanometer on the interface and try to get electronic diffraction directly from the interface. All we can say is that that it has a uniform structure and its density typically 10 to 15% lower. Okay. And it's not like a grain boundary fluctuating. What we even did is we put artificially some holes into these things by etching 1 or 2 crystals out. And what happens is then atoms from the rest of the glass run into these holes. Let me explain it. The way it happens is, what we see, if this interface is stable, what we have done is we have cut a very thin slice out of the nanoglass, like this here, so that we have a glassy region, and then the interface has 2 free surfaces. And we thought about if the interface is a confined state, it could relax into a glass. But the answer was the opposite. It remained the thing, and then when we heated it, the crystals crystallized, and the interface was still there. So the interface could be more stable than the crystals. And the other thing here you see I don't know if it can be seen, here you see the thin slice, and you look through, and you see the glassy regions, and the black stuff is the interface. It doesn't disappear. And the other thing what we did, we took the whole glass and stretched it, and we thought the stretching would destroy the interface. And what you see is you stretch the interface, it remains. And then we heated it, and what you can see here is the thickness of the interface as a function of temperature. It grows a little bit, but then it remains, and the only thing what happens, it crystallizes. So the interface is a non-crystalline structure which is even more stable than the melt-spun glass. But we don't know where the atoms sit, and how the interface knows in which structure it has to go. Once it's in, it never goes out again. Yeah. So at the moment we only can say density and things, and it's very, very stable. And the modulus can be higher, although the packing density is lower.
Okay.
So in the first example you showed, the magnetic properties changes dramatically when you introduce the interface. Now, is that due to interface, or is actually indicating the structure of the nano glass? The glass region itself is also changing. Does the structure of a nano glass change as well?
No, it's the interface. What we do is we first produce the clusters and isolate them from one another by putting an argon layer on the surface so the cluster cannot see each other. So it's a cluster, isolated clusters, isolated by argon. Then we do the Mössbauer spectrum, and we get a very normal Mössbauer spectrum. Then we pump the argon off, and the clusters see each other, at that moment we see the spectrum. And so without any external pressure, as soon as the interface forms, it drops into that deep free energy gap and it remains there. And when we push things together, we get more interface, but we don't change the structure.
Okay.
And even, you know what is surprising, when you put these things together, in the pockets, when three spheres come together, there's a lot of free volume. And what you see is that even in that pocket, the structure is the same than at the point where they touch. So atoms get shifted along the interface. So the answer is it's essentially a two-phase material. A layer between, and what we don't know, what makes this free energy so low of these interfaces.
Okay. Other question? Yeah.
I'm just wondering, where's the fundamental difference between what you're doing there and what people are doing with the thin film physics, where they interface materials to create fundamentally new properties?
Well, if you do the same thing with a very thin film, and you put the thin film together, you also see the effect, but only locally where the thing touches. Whereas here, you get it everywhere. And what we would have thought is, when we shear the material and then heavily deform it, then we don't get the effect. And I think the difference is that when you put these things together, you freeze free volume in a glass. Whereas when you shear it, it's under high pressure and there's not enough free volume. We get a new spectrum, but not the spectrum which we get here. But by thin film, you cannot produce a nanoglass. What you get is you get all dirt trapped in somewhere between. And when you evaporate it on top, then it relaxes and it forms one thick glass layer.
The other question that I have, and where I don't quite agree with you, is you said it would be quite academic to work with something that you can just produce in very small quantities. I mean, in the microelectronics, there are billions of dollars of stuff that you can buy that are in very, very small quantities. So where are the areas where you think this material will have a big impact?
I would have thought, for example, when you want to use this biocompatibility thing, then you would need something in a gram or kilogram. You know, if you want to coat an implant, then a few milligram wouldn't be enough. Or if you want to use these ferromagnetic properties of these materials, then you also need a kilo or something. That's why the application for a structural material. So electronically it would be okay, yes.
Okay, yeah, please.
The quantum transistor is fabricated by the one-dimensional nanoporous structure, right? Since you call it one-dimensional, it should be like the diameter should be very small, and it's still porous. So that means the pore size should be even smaller, right? So in that case, there might be a problem that they are electrolyte. That will be very difficult to enter into the pore, the infiltration of the electrolyte to the very small pores in the nanostructure. So
what I meant by these nanopores, that was this one-dimensional thing, you know. Instead of having, here you have the pores, and you have a three-dimensional charged thing, you know. And now when you go to the other one, you have a one-dimensionally charged situation. That's what I meant by the one-dimensional. It only goes in this direction, and the charge is sitting here, but what controls the electronic structure or the electric properties is this small one-dimensional animal down there. It's not three-dimensional anymore.
yeah, but the pore size is very small on
Well,
the.
it's two atoms. 2, 4, 6, 8 atoms. It's not a whole. There's a difference. You know, in this case, when you go to here, the pore is a three-dimensional hole. And the charge is sitting at the surface of the entire metal. And here is the thing, and the charge is sitting here, but what matters is only this contact region where you have 2 atoms, or 4 atoms, or 6 atoms. That's one-dimensional. So it's not a long row, it's just the contact between the 2 cones. And that forms spontaneously.
Okay, okay then. The second one is about the biocompatibility of the air. There's one slide you show that with the nano glass structure, that the biocompatibility is much better than the ribbon structure, right? I'm not quite sure about my program, because in most cases, you know, if it's nano glass means nanostructure, right? So nanostructure materials should be more like toxic than the bulk size structure, because in most cases for nano materials, they have some structural toxicity, something like this.
No, you see, it's not toxic. The cells grow like mad.
So so why here this nanostructured glass is better, even better than the ribbon? Is there any mechanism behind?
Right. Yeah, but that's not surprising. First of all, the fact is that cells prefer to grow on the nanostructure than on the non-nanostructure. And there are some studies in the literature where it's by the group of Spatz. What he did, he took a crystal and he put small gold particles on it. And then he changed the spacing and the size of the gold particles, and then put a cell on it and asked which spacing and which size gold particles does the cell prefer for the growth. And he finds a very large growth rate when the spacing between the gold particles is in the order of about 4 to 5 nanometers. And he gives an explanation in terms of molecular structure of the cell wall and the substrate. And it's about the same scale what we see here. And the reason why we used a titanium glass is because titanium is not a poisonous material. And so all we can say is when we, instead of producing a uniform glass, a nanostructured glass, the cells prefer it. And of course, you know, this was a single-shot experiment. I'm sure one can find better materials and they would grow even faster. But it reminds one of Spatz's experiments. You know, gold particles are nothing special for a cell. But what he says is, if I don't change the chemistry, I don't only change the size and the spacing of the particles, cells are very sensitive to their reaction. Certain spacing, certain sizes make the cell grow very rapidly. And we seem to get a somewhat similar answer. Because one has to keep in mind, you know, when you have this nanoglass, it's electronically a variation on a few nanometers electronic structure. So it's a chemically the same element, but it's a different electronic structure. And that's apparently what the cell sees.
Thank you.
Thank you. Other question and remark? Yeah. Okay. Yeah, Professor CT first.
Can you tell us why nanoglass have much better ductility? Do you have no mechanistically tell you why the ductility much better? Right. This is what?
What we see in the computer, I can show you. It doesn't help. What we see in the computer simulation is when we take a glass on the computer and pull it, molecular dynamics, then you get a shear bend and the thing fractures. And what we see when we pull a nanoglass out of these interfaces, the shear bends come out, and then they run across the glassy region, and then they end up in the next interface. So these shear bends act as nucleation sites of many shear bends, but very tiny, short ones, and they're stopped immediately. They can never build a big shear bend to fracture, but what we see is it's like a deformation of a polycrystal in comparison to deformation of a single crystal, where you have one big slip lane that fractures, and here we have numerous fine slip lanes. And you can see that. Can you see what happens to the glass? It uniformly dilutes, and here on that surface, if you look in the electron microscope, it's a almost uniformly sheared region. It looks like in a piece of copper.
The ribbon and nanoglass, the thickness same or different?
The thickness was the same.
Same.
Yeah, and the ribbon fractures, one shear and fracture, and here it just strains and doesn't fracture. And on the computer, what you see is that many of these, every interface initiates like a grain boundary, dislocations come out, and here shear bends come out on the computer. But they cannot run across. They can run to the next interface, and then the next interface nucleates new shear bands. And this is consistent with the thing we get here. Such things have been published. People have put small inclusions into glassy materials. And these small inclusions also act as nucleation sites for shear bends, and then it becomes ductile. That has been seen.
It would be very great if you make it thicker, still show this effect or not. Because
A thicker nanoglass.
This is thicker, right? Because the dimension has a thick row and the stability of shear bend. So if you make a thick one, still show this degree.
We have tested up to about 600 micrometer thickness. That's about what we can produce. At the moment, we produce these nanoglasses. This is indicated here. We evaporate the glass, and then we get the glass in helium. Then we get these clusters, and we collect the clusters, and then we consolidate them at high pressure, about 5 to 6 gigapascals. And that's the reason why we cannot produce thicker things than about 500-600 nanometers. If somebody wouldn't mind, this is the way the Inoue group produces them. They sputter it, and they shoot them on a substrate. They get about the same thing, but not centimeters or so. So it's this academic way of producing it. There must be more clever ways of doing it.
Okay, Professor Xu Quan.
Okay, thank you for your excellent talk. So your transistor you introduced remind me that there is another similar structure transistor make use of graphene. And the mechanism of the graphene transistor is that they interpret the graphene as plasma, as a controllable transistor or conductance. So can we understand that your nanoglass is also a plasma or not?
Perhaps it's a different way of saying things. Our problem is, when you want to do any kind of understanding, you have to know we have two kinds of interaction. The interaction between the atoms in the glassy region, and then the interaction in the interfaces. And the trouble is, as we don't know at the moment the detailed structure of the interfaces, we cannot understand that interaction. We can measure modulus, we can measure diffusivity, mobility, but this is always summary. We don't know how far, what the nearest neighbor look like, and what the average spacing, if it's larger or smaller. That is our whole problem. You can describe it that way. It's the same thing, yes.
Other question? Yeah, please.
Thanks for your excellent talk. From your first slides of your talk, especially for AB initio set up the models to calculations, especially for glass interface. So probably the two parts are set up by the glass. So the interface atomistic structure is very important. So what do you think the most difficult things to building up that kind of models for AB initio calculation in the future?
Yeah, this is, if you would know, it's electronically and structurally different. Yeah. So what we have the chemical composition, and we have an average density and everything. But to do solid state things, you always either know the structure or you know the electronics. In this case, we hope that we will know it very soon by having local electron diffraction. Because these very modern instruments like the one which is available in Sendai, and we have one, that you can get a diffraction pattern of about 0.5 nanometer in size. And we hope by these diffraction patterns we can say what kind of configurations we have in these interfaces. In the case, what I showed you, here we have a two-dimensional nanoglass. The question is, we didn't see, what we can see is that we have a lower nearest neighbor number and we have a lower density, but we see, it looks to us like a random network packing. We don't see what is so, but of course this is electronically not different. And that might be the reason why the metallic nanoglasses at least do the same. Now we tried it with one ionic nanoglass, and this was silicon dioxide. We produced very tiny glass of silicon dioxide. And again, we get that answer. As soon as we join them up, we get a silicon dioxide structure which has a lower density and different number of nearest neighbors. But again, we don't know where these nearest neighbors sit.
Okay.
At the moment, we are missing. As soon as we have the structure, we have people to do ab initio, then we would be in good shape.
The last question is, as you proposed in the glassy metals interface, this is very important in the future. And I think thus this proposal is very important to any other kind of amorphous glass, like glassy chalcogenide and metal oxides. They can be like either crystalline or amorphous phases, and especially for multi-layer optical fibers.
Yeah.
They consist of multi-layers of different structures of the amorphous chalcogenides,
yes,
like arsenic selenides, arsenic sulfides.
Yeah.
So that's this kind of a proposal, and then the theoretical systems could be utilized in that kind of system.
There's a whole lot of, you can, with this new approach, you can mix different kinds of chemically different things, but also different kinds of chemical bonds. And so one can make alloys where one can tune the electronic structure. For example, the silicon dioxide, when you have SiO2 molecule, it has to be screened by the conduction electrons that should also have different electronic and optical properties.
Okay.
There's a whole world one can play around with these things. And this is simply not possible when you quench the melt, because in the melt everything is destroyed, and here you just build. It's essentially the sintering technique, nothing else.
Okay, thanks.
Yeah.
Okay.
So you could say that could have been done 100 years ago.
Yeah.
It's true, but that's often true.
Any other question? Oh,
So here you mentioned SAX and the wax.
Here.
Up there. SAX, small angle X-ray scattering, and wide angle X-ray scattering.
Yes.
Can you elaborate a little bit how these techniques can be used in conjunction to look at, for example, the structure of the interface where atoms?
What we look with the wide angle X-ray scattering, what we do is we take the scattering from a melt spun ribbon, and we take the scattering from that one, then we subtract, and we know how much is glass and how much is interface. And then we subtract the scattering from the glass, saying that the internal has a glass structure, and then we get the radial distribution function of the interface. And what we find is that the radial distribution function of the interface is much longer, about 5 times longer correlated than the radial distribution function of the glass. So it's ordered over many of these interfaces. And the small angle scattering, what we do is essentially use the contrast, the density difference between the glassy region and the interface, and that gives us the small angle scattering. And from there, assuming that the chemistry is the same, we can say what the density difference will be.
okay.
That's what, always assuming that you have only 2 elements, the interface, and all the interfaces are the same, and the glasses are all the same.
So let's thank Professor Glenn.